Hello, everyone. Welcome. Hope you're doing well. Hope you had a good Halloween weekend and it wasn't too spooky for you. Um, Someone asked about Veterans Day, and we do not have class on Veterans Day on November 9th. Um, did I assign pre and post lecture videos on that day? I can't remember now. I'll go back and look at that and I'll adjust it as needed. But we will not have class on Monday, November 9th. That's a week from today. Okay. By the way, I got a new mic. How's my sound quality? Is it any better? Yeah?
It's much better.
Great. It's like a big DJ mic right here in front of me. It's like that. Crazy. Okay. Um, good. Yeah, so no class on Monday, November 9th. Our next exam is the following Monday, though, which will be Monday, November 16th. All right. So keep that on your horizon. And that'll be 2 weeks from today. All right. Any questions before we get started today? Excuse me.
Yeah, I have a question.
Yeah.
So if we're not having lecture on Veterans Day, does that mean we're gonna have like our review on the 9th?
Let's see.
Because our exam is the next Monday.
Yeah, you know what? There's not time built in here for a big review in the schedule, but we will have a review on the 11th. Okay. And I'll probably have some available time the following Thursday. So the 11th is a Wednesday. We'll finish up chapter 9 on that day, and then we'll have a review. So that day we'll have both. And then you have the weekend, and the problem set will be due Friday. I'll have a help session. I'll have a question and answers session on Thursday. But I'll send emails about all that as we get a little closer.
Okay.
Okay. I know it's November 11th, but I think the holiday is on November 9th. Am I wrong? Does anybody know when the day off of school is? I think they're giving us the Monday off. Is that correct?
Instead of the Wednesday?
I think so. Is that right? Maybe I'm wrong.
Oh,
I thought we have the Monday off, but I could be wrong. Let me. I can check the schedule real quick. Sorry.
It's on the 11th that we have off. I just checked.
It is on the 11th. Okay, my mistake then. So the syllabus currently has the 9th. So the 9th and the 11th will just switch places. So I'll send out an email clarifying that. I made an error. It looks like I made an error on our schedule. We have the Wednesday off. The Wednesday is the day we have off. I'll send an email out about this, okay? Clear that all out. Sorry about that. Any other questions? Okay, let's get going. We're talking about quantum mechanics, remember? And we spent some time looking at light, and then we learned about the wave nature of particles, right? And we learned about things like the uncertainty principle. And now we're looking at the quantum mechanical model for the hydrogen atom, all right? And what we found is that the Bohr model looks something like this, right? You have orbits in the Bohr model that look very much like planets circling the sun, right? And then you have quantum numbers specifying the orbits. And in the Bohr model, you could only the electron could only be in one of these orbits and never in between, right? The Bohr model ultimately had to be thrown out, of course, because it violates the uncertainty principle. You can't have trajectories like this when it comes to electrons. So that was replaced by the quantum mechanical model. Instead of orbits, we have orbitals, okay? And instead of one quantum number, we have 3. It takes 3 quantum numbers to specify an orbital. It only takes 1 to specify an orbit in the Bohr model, all right? Those quantum numbers and the shapes of those orbitals and their energies are determined by solving the Schrodinger equation, okay? And out of that, you get these orbitals, which are defined by these mathematical functions called wave functions. Each of them has 3 quantum numbers, n, l, and m sub l, plus an additional 4th quantum number that represents the spin of the electron. And last time we looked at these and their relationships a little bit. We also saw that the energy of any orbital is determined by n, the principal quantum number, all right? And E sub n is equal to minus 2.1 times 10 to the minus 18 joules times 1 over n squared. So we can calculate the energy of any one of these orbitals just based on its principal quantum number, right? So the n equal 1 orbitals have this energy, n equal 2 have this energy, and so on. Notice that all the energies are negative. That means when an electron comes into a hydrogen atom, when an electron and a proton come together, right, the potential energy of the electron goes down, right? So if the electron were to fall into the hydrogen atom, it would fall all the way down in this lowest energy orbital, right? And that's a negative number. To take the electron back out, you'd have to put in that much energy, okay? That's why these are negative. All right, I think we covered this last time as well. Each value of L has a letter designation, right? So L equals 0 is S, L equal 1 is P, L equal 2 is D, and L equal 3 is F. And then, there's relationships between each of these, and I think we covered that at the end of last time too, so I'm kind of reviewing here a little bit. For L equals 0, the possible M sub L values are just 0. For L equal 1, we could have possible M sub L values of minus 1, 0, plus 1, okay? This orbital here is the 4s orbital. This, oh, sorry, never mind that. Don't worry about that. For L equal 2, we have these possibilities. For L equal 3, we have these possibilities, all right? So if we put that all together, we get this. Is this, and I think this is where we were at the end of last time, am I right?
I think last time we had gone over the like the different like symbols like N, I.
Right, N, L, right. So N, we talked about the different quantum numbers and the relationships between them, right? So now we're going to put all that together, all right? So for n equal 1, go back and look in your notes. What are the possible values of L?
0.
0. Just 0 is the only possible value of L, right? So for n equal 1, we just have L equals 0. So in the n equal 1 level, and these are called principal levels, right? That are specified by the principal quantum number. And then the values of L specify sublevels, right? So the n equal 1 level has only one sublevel, okay? With the quantum number L equals 0. And then for L equals 0, the possible values of M sub L are only what?
0.
0, right? So, and 0 is specified by the letter S, right? So the only orbital we have in the n equal 1 level is the 1s orbital, specified by this little square right here, okay? Now if we go to the n equal 2 level, right? Then we have two possible sublevels, right? We have the L equals 0 level, and we have the L equal 1 level, yeah? For the L equals 0 level, M sub L, again, can only be 0, so we just have one orbital, and that's called the 2s orbital, right? This is the 1s orbital, this is the 2s orbital. In addition to the 2s orbital, in the n equal 2 level, we have L equal 1 sublevel, right? The L equal 1 sublevel can have values of M sub L of -1, 0, or +1, right? So we have 3 2p orbitals, yeah? And if we keep going up, we find the n equal 3 level, right? That's the next level up in energy. For the n equal 3 level, the possible values of L are 0, 1, and 2, right? So in the L equals 0 sublevel, right, we only have one orbital, the 3s orbital. In the L equal 1 sublevel, we have 3 orbitals, the 3p orbitals, right? But now because L equal 2 is also a possibility in this level, in this n equal 3 level, we also have the d orbitals. And why are there 5 of those? Because for L equal 2, M sub L can be equal to -2, -1, 0, +1, and +2. All right? Does that make sense? All right. All right, let's see if you're getting this. Let's see if you can answer this question for me. Let me start a poll here. answer that question for me. Okay, about 10 more seconds. 10 more seconds to get your votes in. Five, four, three, two, 1, 0. Okay, so the correct answer was E. And so most of you got that, but some of you choose D and A. Let's see. M sub s. So M sub s is the spin quantum number. And remember, it can have values only of +1/2 and -1/2, and that's it. Those are the only two possible values for M sub s, okay? And a few of you put A. M sub L must be greater than or equal to L. So M sub L can only go from -L through 0 to +L. So in this case, right, if L equal 1, what are the possible values of M sub L? Anybody?
-1, 0, and 1.
Correct. -1, 0, and 1, right? So that's the problem here. You can't have an M sub L of -2, right? That combination is not allowed, all right? So only certain combinations are allowed based on those rules that we covered last time, okay? All right, any questions on this? Is that clear now? Pretty much. Okay, let's see if you can answer this one. Go ahead and try this one. I really encourage all of you to participate in these questions because remember, learning is not passive, right? You learn when you're active. When you're answering the question, you're actually building those neurons. It's helping you to learn, right? Even if you answer it incorrectly, you're still building those neurons. So be active in the process. I really encourage you to participate. Most of you do, but a few of you I see don't really participate. And it's just better for you if you do. All right, about 10 more seconds. right. So the correct answer there was D. And again, most of you got that, but a few of you put B, which is a pretty close guess. So remember, when you write the notation this way, right, this gives you the principal quantum number, and this gives you the value of L, right? And for L, remember, you got 0, 1, 2, all the way up to n minus 1 is possible. And these are each assigned a letter, right? 0 is assigned the letter S, 1 is P, 2 is D, and 3 is F. Okay, S, P, D, F. So since L is equal to 1, right, and N is equal to 3, that's the 3p orbital. Okay?
I have a question.
Yep.
Okay, so I'm looking at the chart where it shows the N. So when the L is equal to 0,
Hold on, Diana. Somebody else is. Oh, is that your background noise? I can't quite understand you because maybe there's some background noise.
yeah, sorry.
Try again, or you can text it to me, or you can send it in the chat box. Yes. So these are the designations right here. L equals 0 is always S. L equal 1 is always P. L equal 2 is always D, and L equal 3 is always F. Okay. All right. So we got that. All right. So now we'll look at a couple of other things. The first thing we're going to look at is the energies of these orbitals and how those energies help us to explain atomic spectra. All right. So those atomic spectra, remember, that we looked at last time. Remember atoms that if you have an element, a sample of an element in the gas phase, and you excite it with an electrical current, the electrons get excited at higher levels, and then they come back down and they give off light. All right. So something like this. Let's say the electron is excited from n equal 1 to n equal 3, and then it relaxes back down, and when it relaxes back down, it gives off a photon of light. The important thing to understand here is that the energy of that photon of light is going to be exactly equal to the difference in energy between these two orbitals. Okay, so that photon of light is going to take out how much energy? The energy difference between these two. So that means that for a given energy difference, that energy difference is going to determine the wavelength of that photon, right? Because remember, the wavelength of a photon, we learned this, E is equal to hc over lambda, right? If you have wavelength lambda, that means the photon has energy E, right? So you can see that we have all these transitions in the hydrogen atom, right? From when the atom goes down from a higher state to a lower state, it gives off energy. When it goes up from a lower state to an upper state, it absorbs energy. Okay, so this process absorbs energy, this process gives off energy. And then depending on the energy difference, right, it's going to give off light of different wavelengths. The ones that are visible are these, okay, but it also gives off some infrared wavelengths and some ultraviolet wavelengths. Let's do an example of how we would calculate those wavelengths given what we know about the quantum mechanical model for the hydrogen atom. All right. So in this example, we're going to find the wavelength of light emitted when an electron makes a transition from 3p orbital to 2s orbital. All right. Now, the only thing that really matters here, because the energy only depends on n, right? The only thing that matters is the difference in n. Okay, so what we're saying is that if you look at the energy levels, this is E1, E2, E3, right? We're looking at this transition from 3 to 2, right? And then it's going to give off light, and we want to find the wavelength of that light. Okay. We'll look at that question about the n equal 1, but for hydrogen, yes, for hydrogen atom, which is all we're talking about right now, just the hydrogen atom, the n=1 orbital is the lowest energy orbital. So the electron will eventually always find its way back down to that one way or another. Okay. All right. So what we want to do is set up the problem. We know that for a given value of n, E sub n is equal to negative 2.18 times 10 to the minus 18 joules times 1 over n squared. Right? And so what we want to do is we want to say, okay, so what's the difference in energy between the two orbitals? So remember, we're going to do delta E. Remember, delta anything is always final minus initial, right? So this is E final minus E initial, right? And E final is E, it's going from 3 to 2, right? So that's energy of the n=2 orbital minus the energy of the n=3 orbital. Okay. So that's going to, so the energy of the n=2 orbital is minus 2.18 times 10 to the minus 18 joules times 1 over 2 squared, right? Minus the energy of the E=3 orbital, which is minus 2.18 times 10 to the minus 18 joules times 1 over 3 squared, double brackets, right? Does that make sense so far? Okay, so then we can, so you can calculate this out, and that turns out to be equal to minus 3.03 times 10 to the minus 19 joules. Now, why is the energy negative? Who can answer that? Why is the energy negative here?
It's
Because it's being released.
Being released. Correct. It's being released. It's going out of the system, right? And because it's going out of the system, it's like a withdrawal from the checking account, right? So it's negative. Now, the energy of a photon is always going to be positive, right? So we're going to plug into this equation, E is equal to hc over lambda, to find the wavelength of the photon emitted. It's always going to be positive. If the photon is absorbed, right, then delta E will be positive. If the photon is emitted, then delta E will be negative. But the energy of the photon is always positive, all right? So what we're going to do then is solve this equation for lambda. Lambda is going to be equal to E over hc, right? And then we're just going to plug into there, right? Because we already know the energy, except we're going to use the positive version of that, right? So it's going to be 3.03 times 10 to the minus 19 joules.
Isn't it the other way, the equation?
Yeah.
Sorry?
E over E?
E.
Is it lambda equal to
Yes.
HC divided by E?
Sorry. Thank you. HC over E.
Good catch, Javier.
Nice. All right, so it's HC. I have it correct in my notes. I just wrote it down here. Okay, so 6.626 times 10 to the minus 34 joules second. See, I love that because I can tell you guys are paying attention. That's awesome. Thank you. Was that Javier? Was that you? Thanks, Javier. 3 times 10 to the 8th meters per second, right? HC divided by E. 3.03 times 10 to the minus 19 joules, right? So look what happens to units. Joules cancel, seconds cancel, right? And you're left with meters, right? Which is a unit of wavelength, right? So when you calculate that out, you should get 6.56 times 10 to the minus 7 meters. If you convert that to nanometers, that's 656 nanometers, right? So that's how you do that kind of a problem. We basically just calculated the wavelength of that light right there. Does that make sense?
I have a question.
Yeah.
So since HC is like always going to have the same two variables, why don't they just do that as like one number?
Oh, you could, but since they're different constants that have values that are not always used together, you'd have to make up like a new constant there. And as much as possible, we try not to do that.
Okay.
Okay. I think there's a couple other questions here. Was that you, Emily? Oh, Emily, did you have a question?
Yes, I just wanted to clarify. So it seems like if we were to do that calculation, we would get, oh, I see. So you just used a positive change in energy
Correct.
because our answer needs to be positive.
Well, yeah, because the energy of a photon is always positive. So the negative sign comes in delta E, and a negative delta E tells you that the photon was emitted from the atom. A positive delta E tells you that a photon was absorbed. But the photon itself always has positive energy,
Okay,
right?
got it.
Point
Yeah.
of the view of the atom, right? Delta E. So in other words, the surroundings, if you were doing the surroundings, then delta E would be the opposite sign. But this is the photon itself. This is kind of like the money itself that's being transferred, right? The money itself, if it's going in, it's positive. If it's going out, it's negative. But the money itself is always positive money,
Okay,
if you will. Okay.
got it.
Taylor?
Just a quick question. Can you simplify the equation to just be negative 2.8 times 10 to the negative 18 joules and then times the difference?
Yeah, absolutely. Yeah. So you
Okay.
you can factor, notice, you can factor that guy out of the equation. Oh, sorry.
Yeah.
Oh, no, no,
Okay.
just that part, right? You can
Okay.
factor this out in front, and then you would just have negative 2.18 times 10 to the minus 18 joules, 1 minus n final squared minus 1 over n initial squared.
Okay.
So you can do
Okay.
it that way too. Yeah,
Okay.
absolutely.
Thank you.
Alex?
This might be jumping way ahead, but isn't a photon technically like an interaction, not like a physical thing?
Ooh. Good question. Complicated answer, but right now we could think of photons as individual particles of energy, packets of
Okay.
energy whose energy is determined by wavelength lambda. Okay.
Cool.
All right. Okay, here's a question for you. This is not a calculation. It's kind of a concept question involving the calculation we just did. So let's see if you can get this one. All right, 10 more seconds. All right, the right answer is A, which most of you got right. Nice work. Let's see, what was the other? So basically, the bigger the energy difference between the two orbitals, right? The larger the quantum of energy released. The larger the quantum of energy, the wavelength.
The shorter the wavelength?
Exactly right. Exactly right. The bigger the quantum of energy, the shorter the wavelength, right? So remember those relationships. But notice that the n equal 3 to the n equal 1, right, which is this one right here, in terms of energy, notice that that is the most space, right? It's the longest arrow here, right? N equal 4 to N equal 3. Notice is that tiny little arrow right there, right? N equal 1 to N equal 4 is a longer arrow, but notice it's saying would release the largest amount of energy, right? So this would absorb a lot of energy, but it wouldn't release any, right? And then lastly, N equal 2 to N equal 1 is this one, and that's shorter than this one, right? So the right answer is A, and most of you got that, so nice work. Okay. Good. Any questions on that?
Yeah. Why is n equal 2, like the difference between n equal 2 and n equal 1 so substantial? And then it just gets smaller and smaller as it goes up.
Yeah, it's because of the relationship, right? The relationship is this. So it's an inverse n squared relationship. And so as n gets bigger, the difference between levels gets smaller.
Okay. Thank you.
Right.
Yeah, I should have thought that. Okay.
And in fact,
Is it like gravity?
at n equal infinity, right? At n equal infinity, right? That goes, then it's 0, right? So in other words, we're taking 0 to be the electron completely pulled away from the proton, right? And as it gets closer, it drops in potential energy, right? And that's why the energy is negative.
I feel like that's analogous to gravity.
Yeah, you can kind of think of it that way. Yep. Okay, very good. Nayeli, did you have a question?
Yeah, so just to kind of summarize, you said that the larger the quantum of energy, the shorter the wavelength.
Correct. And that's because of this relationship, right? E is equal to hc over lambda. So as E gets bigger, lambda gets smaller.
Okay.
Right?
And then
'Cause they're inversely proportional. Pardon me?
if the transition of between n levels is shorter, so like for example, on n equals 2 going to n equals 1, then you have a larger wavelength.
Correct. So notice these, right? These are in the visible, but then if you go towards shorter energy, less energy differences, then those are the infrared, right? Longer wavelengths. If you go towards bigger energy differences, then those are shorter wavelengths. Those are ultraviolet. Does that make sense? Abe?
Yeah, just to be clear, whether the sign of delta E doesn't really impact the sign of that energy, right?
Correct.
Okay.
This E is always positive.
All right.
Okay. In this equation, this E is always positive. The sign of delta E only tells you whether the photon is being absorbed or emitted. Absorbed, delta E is positive. Emitted, delta E is negative. But the energy of the photon is always positive.
All right. Got it.
All right. So let's have, I think in the interest of time, I might have to skip this question. So I'm going to skip it. Actually, I'm going to put it in here for the sake of the recording. And so if you guys want to come back and do it later, you can. But I'm going to pause here for a minute. This is basically just repeating the calculation we just did, but from n equal 3 to n equal 5, and then finding the wavelength. Okay. So I'm going to pause for a minute. And if you did that correctly, the right answer is A, 1.28 times 10 to the third. Okay, so you guys can come back to that later if you'd like, but just in the interest of time, I'm going to skip it for right now. Maybe we might have time to come back to it, actually. Well, we'll see. Let's talk a little bit about the shapes of these orbitals. So now we know what the orbitals are. Let's go back to this image because this kind of helps us to see them, right? When we put together those three quantum numbers, we get a set of orbitals, right? The 1s orbital down here in the n equal 1 level, 2s, 2p orbitals, 3s, 3p, 3d orbitals, right? We now know the energies of those orbitals. Notice that for a given value of n, all the orbitals that have the same value of n have the same energy, okay? We say that those orbitals are degenerate. What does that mean? Just means they all have the same exact energy. So the n equal 1 level, there's only one orbital, and it has this energy, right? Energy is E sub n is equal to minus 2.18 times 10 to the minus 18 joules, 1 over n squared, right? So since n equal 1, it just has energy equal to that, right? And then for n equal 2, all three of these orbitals, the 2s and the 2p, all have the same energy. For n equal 3, the 3s, the 3p, and the 3d all have the same energy, okay? What we'd like to do now is say, okay, well, what do these orbitals look like, right? For the Bohr model, we knew their energies and we knew what they look like. They look like this orbit around the nucleus, right? But what do these orbitals look like? Well, remember, they're not going to be trajectories like this, right? Because for an electron, we can't really specify a trajectory like that. So what are they instead? What they look like, what we can tell about them is a probability density map. A map that tells us the probability of finding them in a certain area of space. So let's look at let's see what they look like. So here's the 1s orbital, okay? That one that's lowest in energy. And the way I'm representing this is a couple of different ways. One is to be able to plot psi squared, the wave function squared, which is probability density. Is basically probability per unit volume. Probability density is probability per unit volume, all right? And we see that if we plot probability density as a function of r is the distance between the nucleus, right? The distance away from the nucleus. Right at the nucleus, the probability density is very high. And then as you move away from the nucleus, it drops off exponentially, okay? Another way to represent it is with this dot density representation. So you can think of this in the following manner. Suppose you were looking at a hydrogen atom in the dark and you had a camera and every second you took a picture of it, right? So you'd see the nucleus. Let's say the hydrogen atom wasn't moving, so the nucleus would always be in the same place. But every time you took a picture of it, right, you'd see the electron. So the electron in one picture would be here, another picture would be there, another picture would be there, and so on. And you do this thousands of times. And every time you take a picture, you make a composite sketch of all of those together, right? And you would get something like this, all right? So remember, we can't set up a trajectory to understand how the electron moves in this space. In a sense, when we're not observing it, it's kind of like the double slit experiment. It goes through both it goes through both slits, the electron. Similarly, when it's not observed, the electron is everywhere. It's all over this place, right? But when we observe it, we force it to be localized in one spot. We basically force it to be a particle. And one time we'll see it here, another time we'll see it there, another time we'll see it there. And if we do that thousands and thousands of times, we'll get a distribution that looks like this. Does that make sense? So this kind of gives you an idea of where the electron is sort of spending its time, right? It's spending a lot of time here, less time here, less time here, less time here, and no time out here, right? You won't find it out here, really none of the time you'll find it out here, right? Because the probability, notice, goes to 0 as you get farther and farther away from the nucleus. The speed of the electron is another issue altogether. We don't want to think about this as the electron going from here to kind of zipping around. That's the wrong picture. The idea is that the electron, when we're not looking at it, is in this whole area as a wave, right? When we take the picture, it localizes in one spot. Just like in the double slit experiment, when the electron was going through both slits as a wave, it was essentially in two places at once, right? It was going through both slits and interfering with itself. Why? Because it was behaving like a wave. Similarly, this is actually a three-dimensional wave, and the electron is everywhere in this area when you're not looking at it, but when you look at it, you localize it and you force it to be in one spot and one spot only. All right, so that's more the correct way to think about it. Yeah, it's really weird. The electron actually here. So when you think about an electron orbiting a nucleus, right, it has angular momentum because it's moving around. It has some velocity, right, in the Bohr model. Here, it has no angular momentum, believe it or not. So actually, here's the interesting thing. If quantum mechanics wasn't the way it was, the hydrogen atom, we wouldn't really be able to explain why the hydrogen atom is stable. And here's why. In a sense, the reason you have stable planetary orbits, like orbits around the sun, right, is because the planet is moving in this orbit and it's attracted by gravity, and the combination of that, right, there's a force that keeps it orbiting, right, but it prevents it from being drawn into the sun. If you had a sun, right, and you had a planet right there, and the planet wasn't moving, what would happen?
It would just fall into the sun, right?
It would just fall into the sun, right? It would just fall into the sun if it didn't have any angular momentum. Well, here's the weird thing. The electron in the hydrogen atom has no angular momentum, right? Because if it had angular momentum, you'd be able to measure that, and we can't. The angular momentum is 0, right? So the electron, if it wasn't quantum mechanical, would fall into the nucleus, and all matter would be destroyed. Matter would not be stable. So the reason it doesn't fall into the nucleus is because it's a wave, all right? And as you make the wavelength of a wave shorter and shorter, right? We know that its energy goes up and up and up, right? So this is a balance between the energy of the electron on the one hand, which goes up as you confine it, and the pull of the nucleus, which is pulling the electron in, right? And so if we didn't have that wave nature, hydrogen would just collapse. Anyway, that's just a fun fact. All right, let's see. So remember, the density of the dots is proportional to the probability density, right? So the probability density is high here and lower out here. Okay. In this representation, the height of the curve is proportional to the probability density, right? And it looks like that, all right? There's a third way we can represent an orbital, and that is with a three-dimensional surface like this. And this surface represents the sphere within which the electron will be found 90% of the time. So in other words, this surface would maybe, you know, on this plot would fall right around here, right? And it indicates that 90% of the time the orbital is, the electron is within this sphere. Okay, so that's another way to represent these orbitals. All right, now here's the part that's a little more complicated that we need to understand at least a little bit. Megan, do you have a question?
Yeah, it was back regarding the I think the previous slide, the that one, yeah. So we were talking about how like the placement of the electron kind of shows like how long or short the wavelength is, I guess.
So if you think about, let's think about this. If you think about a wave on a string, right? You have amplitude and x here, right? And you can have a wave like that, or you can have a wave like that, right? On the same length string, you can have a wave like that. So this one is lower energy. When things are quantized in quantum mechanics, right? The shorter the wavelength, the higher the energy. So this is lower. This is the lowest energy. This is the next lowest. This is the next lowest, and so on. So this is kind of like analogous to this orbital, right? It only has positive phase, and it's the lowest energy orbital. Am I answering your question?
Kind of. I guess I'm more wondering, so the pictures that we're taking, or like if we were to take those pictures every second,
yeah,
the distance from the nucleus to the electron is always changing. So even though it's moving, it's not the same like distance.
Exactly right. Yes. One time, you take a picture and the electron would show up here. The next picture would be over here. The next picture would be over here. The next picture would be here, right? So it's kind of like, remember when we talked about this? Let me go back here. remember we talked about the sort of quantum mechanical baseball, right? We can't predict a trajectory for where the baseball is going to cross home plate if it was quantum mechanical, right? But what we could do is if we saw many, many pitches over time, we could create a density probability kind of like this. It says, okay, within this circle, 20% of the time it'll be in there. A bigger circle, 40% of the time it'll be in there. This big circle, 70% of the time it'll be in there. So that's kind of the analogy that we're trying to draw for the orbital. Does that help? Great. Okay. Okay. Let's see. All right. So now this part is a little trickier to understand. So this is called the total radial probability. And this is the same exact orbital. Okay. Remember, this plot was just probability density. All right. But remember, probability density is probability per unit volume cubed, or per probability per unit volume, which is per space cubed, per meter cube, centimeter cube, whatever unit you want to use. Probability per unit volume. That's what this is. This plot is total radial probability. So total radial probability is equal to the probability density times the volume of a thin spherical shell with radius r. Total radial probability is probability density times volume of a thin spherical shell with radius r. Because so notice, probability density, probability per unit volume times volume, right? That gives you actual probability. Okay, it's kind of like density. So let's say grams per centimeter cubed. If you multiply that by centimeters cubed, what do you get?
You get grams.
You get grams, right? So if you take probability density, which is probability per unit volume, and you multiply it by volume, then you get probability. Okay. But why does this curve look like this? And it's actually important to understand this for where we're going. This curves look like this because remember, it's probability times volume of this thin spherical shell. All right. So probability is going like this, right? Psi squared, the wave function squared is a function of r. But the volume of a thin spherical shell as a function of r is going like that. And here's how you can think about it. The volume of think of this volume of a thin spherical shell kind of like you would an onion. So think about an onion, all right? And think about how much onion you get as you get closer and closer to the middle of the onion, all right? So you have in the middle of the onion, you have little pieces, right, like this. And then if you go a little further away to a bigger radius, right, you have a little bit more onion and then more onion and more onion, right? So if you wanted the volume of the thin spherical shell of onion, right, where would you get more volume? Near the middle or outside near the edges?
Edges.
Near the edges, right? Think about cutting up an onion, right? And these pieces out here, these little shells of onion, have more onion in them, right, than the ones in the middle, right? Because as the radius gets bigger, the volume of that thin spherical shell, even if it's the same thickness, has more volume. Okay? So that's why the volume of the shell as a function of r goes up. So you multiply this by this and you get something that looks like that. Okay? Notice that the total probability of finding the electron at the nucleus is 0. Why is that? because the volume of an onion shell, right, at the very center of the onion is 0. There's no volume, right? If R is equal to 0, the volume of that thin spherical shell is 0, right? But as R gets bigger and bigger, the volume of the thin spherical shell gets bigger and bigger, right? And so you have this multiplied by that, and you get something that looks like this, okay? So the maximum probability really occurs here at 53 picometers away from the nucleus, right? And then it drops off after that. Does that make sense? Do you have questions on this? Abe.
Wait, so basically these graphs are telling us like the further that we get away from the radius, the volume increases, but the probability density decreases.
Correct. That's exactly
Got
right.
it.
And then
And then
multiplied together, you get something that peaks right here and then goes back down.
okay,
When you multiply this by this, because the exact shape depends on how fast this falls off and how fast this goes up. And
Yeah.
we're not going to worry about that too much, except to say that when you multiply this by this, you get this.
okay.
Taylor?
Yeah, I just wanted to. So if you increase the layers of the onion,
Yeah.
right, and get it bigger and bigger, your probability is still kind of the same. So that's why it goes up and there's like a peak, right? Like if you have
Right.
your ball. So that 52.9 picometers is the like best blend of both of them,
Exactly.
if I understand it.
That's where this
Okay.
is still pretty high, but this has actually got some significant volume to it,
Okay.
right? So the
Okay.
important thing to understand is that this probability density goes down, but the volume of a thin spherical shell increases as the radius gets bigger, just like the amount of onion in a shell of onion gets bigger as you get further away from the center of the onion, right? Just think of the volume of onion, the amount of onion you would get from that little shell of onion. Let's see. Did you have another question, Abe?
Yeah, just one more question. How did they figure out that was like, I guess, the peak?
Oh, so these are all, I mean, if you ever take physical chemistry, you'll like look at these functions and you can just multiply, you can do all this. This comes right out of the theory. So you solve this equation, you get a set of functions, right? You solve the Schrodinger equation, where to go? You solve this equation, you get a set of functions psi, you can make plots of them, you can multiply, you can calculate this volume, right? This is all easily, I mean, it's not easily, but you can do it. And you can multiply them together and you can calculate, this is all theoretical. And it turns out it's exactly correct, right? So when we look
Whoa.
at the hydrogen atom, it in fact has this kind of distribution.
Okay.
Yeah, so this comes about from basically multiplying two functions together and then graphing them.
Yeah.
Okay. The other thing I want you to understand about these functions is that they could have what are called nodes. All right. So remember, for a wave, a node is fairly straightforward. We kind of understand what a node is. A node is when the wave goes through zero. Okay. So you could also have you can have nodes in these wave functions. All right. On the hydrogen atom. So remember, this was the 1s orbital, okay? If we plot the 2s orbital, the probability density looks like, well, I should, if you plot the wave function, psi, it goes like this. All right? Notice that this is the wave function as a function of r. So as you move away from the nucleus, you have this node. What's a node? A node is where the wave function goes through zero, because remember, these are waves, yeah? So a node in a wave function is just like a node in a string, right? It's where it goes through zero. The weird thing is when you square this, right? When you do the wave function squared as a function of r, then no negatives because it's all positive, but this is what represents probability density, all right? So notice what you have. When it goes through 0, you have a node right there. What does that mean? That means you can find the electron in this area and you can find it in this area, but you're never going to find the electron at the node. All right. When you take your pictures in this case, the electron will never be right there, right at that node. And then this is total radial probability again. When you multiply the probability density times the volume of a thin spherical shell, you get a plot that looks like this. Okay. And notice that you have a little area here near the nucleus where you can find the electron, where the electron appears some of the time. And then you have a node, the electron is never found there. And then you have another area of probability where you find the electron. Okay, and then it goes up. Just like we go from this one to this one to this one. As you go up in energy for the 2s orbitals, you go from having 0 nodes in the 1s orbital to having 1 node in the 2s orbital to having 2 nodes in the 3s orbital. Okay, so this is 2s. For 3s, it would look like this. The wave function goes shoot, shoot, shoot. Okay, and the wave function squared, right, takes away the negative, so it just goes boom, boom, boom. I didn't draw that very well, but it looks like this. Notice what you have here now. 1, 2 nodes. Okay, so no nodes in the 1s wave function, 1 node in the 2s, and 2 nodes in the 3s. All right, those are areas of 0 probability. Of course, from the 1s to the 2s to the 3s, what happens to the energy of the electron in that orbital?
It's increasing.
Yeah, it's increasing, right? It's increasing because and the wavelength is shorter. It's having more nodes. Okay. Okay, so that's the 1s, 2s, and 3s orbital. Now let's look at the 2p orbital. Okay, the 2p orbital has a very different shape. It looks like this. If we just plot the total radial probability as a function of distance from the nucleus, it goes up and then goes back down. But it's not uniform all the way around the way the s orbital was, right? It's oriented along only, in this case, the x-axis for the px orbital, right? Because remember, there's 3 p orbitals. And so the probability density is very high right there and very high right there. We say that it has 2 lobes. In the middle is a node. Just like there was a node here. This is a radial node. There's a node here in the middle as well for the 2p orbital. Okay. The other 2p orbitals look like this. So there's px, which is oriented along the x-axis, py oriented along the y-axis, and pz oriented along the z-axis. The 3p orbitals, if we were to plot those, they'd look, let me go back. Notice, I wanted you to notice 2 things about the 1s, 2s, and 1s, 2s, and 3s. As you go from 1s to 2s to 3s, you go up in energy, you have more nodes, and the orbital gets larger, right? Can you see that, right? You can't really see the 1s because it's not here, but the 1s would be smaller, right? So you have 1s, 2s is bigger, higher energy, more nodes. 3s is bigger yet, higher energy, more nodes. Similarly, if I was to plot the 3p, 4p, 5p, we'd see the same pattern. Have the same basic shape, but it'd be bigger, higher energy, and more nodes as you go to higher value of n. Okay. All right, now we get to the d orbitals. The d orbitals, L is equal to 2, right? So you got L equal -2, L equal -1, 0. So you got 5 of those, right? For the p orbitals, L is equal to 1. So we have -1, 0, and +1. For the d orbitals, we have 5 values of m sub L, right? So we have 5 d orbitals, right? And they look like this. Notice they have more of these what are called angular nodes, right? Where the probability goes to 0. So you have a node here, you have a node here, and you have a node here, and you have a node here, right? As you go, or I guess you could just think of that as two nodes, one here and one here. Similarly for these other ones, you have those kinds of nodes as well. These have 4 lobes instead of just 2, okay? And they have different orientations depending on which of the 5 orbitals we're talking about. So 4 of them have the same shape, just different orientations. This one is oriented in the X, the one that's the DYZ is oriented in the YZ plane. So this is the YZ plane. DXY is in the XY plane. DXC is in the XC plane. DX squared minus Y squared is in the XY plane, but instead of being between the axis, the lobes are on the axes. All right. These aren't huge details you have to worry about too much. I basically want you to be able to recognize these different types of orbitals, right? I want you to know this is the P, this is the D, right? And this is an S. All right. And then the DZ squared orbital is like kind of a funny, completely different shape than the other 5. All right. Just for fun, here are the F orbitals, right? So remember we got L equals 0, 1, 2, 3, 4, right? That's S, P, D, and F, right? So there's 1 S orbital, 3 P orbitals, 5 D orbitals. How many F orbitals?
Is it 7?
7, right? 7. Okay, yeah. Someone said that all they see is these balloon animals. Remember what these represent. This represents where you find the electron, right? That's telling you that the electron, you find it here, here, here. This kind of looks like one of those suckers for a baby, right? What do they call it? Pacifier?
Yeah, Pat.
Kind of looks like a pacifier. But anyway, these are the d orbitals, just for fun. Okay. This is a question for you guys. Go ahead and answer that one.
Hey, Professor.
Yeah.
For some maybe it's just me. There's no letter corresponding to what.
Oh,
So I don't know what.
You're right. Never mind. My bad.
Yeah, same.
My bad. I see what you mean.
I'm wondering the same thing.
Oh, someone figured it out though. They actually. I'll just ask the question. What type of orbital is this?
D.
A D.
Pick D and have it be letter D. Yeah.
Yeah, that's what I did.
Yeah, happens to be letter D. Some of you were clever about that. Okay.
It's genius.
All right. Let me say one other thing about nodes and something called phase. All right. So when you have a wave, right, we say that this is positive phase and this is negative phase, right? And that makes sense in a wave on a string like this, or a wave on the surface of water, right? You can understand positive phase and negative phase. So it turns out that these orbitals also have phase, positive phase and negative phase. So for example, the S orbital is all positive phase. So it's kind of like this kind of a wave, right? It's all one phase. When you look at the 2s orbital, it actually changes phase from here to here. This is positive and this is negative phase. All right? Because remember, these are 3-dimensional waves. And we'll see later why phase is important, but for now, I just want you to understand that it exists, okay? And I want you to understand that the s orbital, the 1s orbital, is all the same phase, but that the p orbital changes phase from one lobe to the next, because this is like a node, right? So it changes phase from positive to negative from here to here. I know this is a little hard to understand in 3 dimensions because it's hard to understand what a 3-dimensional wave is, okay? But they still have in math, you can have as many dimensions as you want, and you can have phase in the orbitals, right? And so these orbitals have phase. This is positive phase, this is negative phase. We're going to see that this is important a little bit later. Okay. All right. And yeah, that's the, oh, okay. So that's the end of chapter 8. Do you have any questions? So no questions. Let me go back and have you work this problem. See if you can do it. I already gave away what the answer was, but go ahead and try to work this problem, and then I'll work it for you too, just so you see how it's done. I have a question. Do the positive and negative phases correspond to polarity? The answer is no. So the electron, let me just start this. So polarity is something different. Polarity relates to differences in electron density, but for a p orbital, right, this is positive phase. Let's say that's negative phase. The probability of finding the electron here is the same as here, right? Because these two have the same shape and everything. They just have this different phase, which is, again, it's sort of hard to explain in 3 dimensions, but the best way to think about it is by analogy to phase in a wave, right? Where this is positive and that's negative. It's kind of the same idea. All right, I'm going to put up this so you have those equations, how we did it last time. And let's see if you can go ahead and try to do this problem. I had another question. So the number beyond 4 does not have a letter. It actually does have a letter. It's S, P, D, F, and then it goes G and H. So they keep going, even though those are very high energy orbitals. Abe, did you have a question?
Yeah, I don't know if you could, but could you go back to when you were explaining like the orbitals and like
Yeah, let's do this question first, and I'll come back to that if you don't mind.
okay.
I think it's not possible to change my answer after I've submitted it, right?
Yeah, you can change it.
Huh?
Yeah, you can change it.
Okay, can I change it?
Go ahead. Does it not let you?
I don't know how I would change it.
Oh shoot. Maybe you can't change it.
Okay.
I thought you could. I thought it'd let you, but it doesn't. Huh? It doesn't give you an option. Okay. Sorry about that. I don't think I can do. I don't think I can allow. I have no way to allow it either on my end. Okay, looking good. I'm gonna end it in just like another 10 or 15 seconds. All right, so the right answer was A, which most of you got, so nice work. Just really briefly, for those of you that didn't quite get there, delta E, right? In this case is the energy of the fifth level, right? Always final minus the energy of the third level, right? Final minus initial. Who was it? Was it Taylor that said you can factor out this if you want and write it in short? Or was that Abe maybe? You can factor this out and write it in shorthand notation like this, right? So you can do that, or you can just do the calculation this way. Either way is okay. But either way, you find out the delta E is equal to negative 1.55 times 10 to the minus 19 joules. Sorry, positive. Positive 1.55 times 10 to the minus 19 joules. Why was this one positive where this one was negative? Right? Why does this one come out positive?
Because energy is being absorbed.
Exactly. Okay, the energy is being absorbed, right? So that's why that one's positive. In this case, the energy is being given off, so that's why that's negative. But in both cases, the energy of the photon, right, is always positive. So this E gets put into this equation down here, right? And you put in H and C, and you get nice cancellation here of units, right? And you get seconds, where the seconds cancel here and here, right? And you end up with meters, right? So you end up with 1.28 times 10 to the minus 6 meters, which is 1.28 times 10 to the third nanometers. All right. All right. Questions, comments, curses? The next thing we're going to start doing is writing electron configurations for atoms. And what we want to know now is, okay, well, is there a way we can specify where an electron is in an atom and what kind of orbital is an electron in an atom? So, for example, for hydrogen, we would write the electron configuration at like this, 1s1. And what this means, so this is electron configuration. This represents the orbital, right? And this represents one electron in that orbital. Okay. And we call this the electron configuration. We say when hydrogen is in its ground state, and the ground state is the lowest energy state. We know that the electron is in a 1s orbital. All right. What are the 4 quantum numbers for this electron? Who can give them to me? N equals what?
1.
1. L equals
0.
0. M sub L equals
0.
0. And then we have M sub S, which is not clear from this notation whether it's plus 1/2 or minus 1/2, right? So we can specify that with something called an orbital diagram. And the orbital diagram for the hydrogen atom uses a square to represent the orbital, okay? And then it uses a half arrow to indicate the electron. And a half arrow pointing up is M sub S equal plus 1/2. And an arrow pointing down is M sub S equals minus 1/2. All right.
Can you figure up a little bit? Sorry.
Sorry, my bad. An arrow pointing up is M sub S equals plus 1/2. Arrow pointing down is M sub S equals minus 1/2. All right. So the 4th quantum number in this case would be what? Plus 1/2. Right. If we wanted to write an electron configuration for helium, we'd have to know a few more things. Okay. And if we wanted to write it for lithium and beryllium and all the rest of the elements, we have to learn a few more things about how these orbitals fill and also how the energies of the orbitals change from the hydrogen atom to other atoms. Okay, so that's what we'll tackle on Wednesday, right? That's what we'll tackle on Wednesday. Okay. Any last minute questions or comments? Is the sound quality significantly better? Sweet. So glad to hear that. Okay, so we'll have this sound quality for the rest of the semester and next semester as well. So that's kind of nice.
Yeah.
We just the small little things, right? We'll take it. All right. Thanks, everyone. I hope you have a great afternoon and a great evening, and I'll see you all on Wednesday. Thanks for coming.
Thank you.
Thanks, you guys.
Thanks, Joe.
Thank you, Professor.
Thank you. I'll stick around, of course, as usual, to see if people have questions.
Can you move your paper a little bit more to the top so I could see the bottom?
Yeah.
Thank you.
Let's see. Megan has a question.
Hi. I don't know if you would be able to go back and explain the where did it go? Like the S, P, and D orbitals. I'm still like shape-wise, I'd be able to differentiate them, but I'm still very lost.
Okay. Are you thinking of in terms of the quantum numbers? Or
No, you had like for the S1, it was the slide, there was like the graphs. There was like I could not.
What does that mean? Yeah. So what I'm trying to show here, so this is the kind of the spherical representation, right, where the electron is found within that sphere 90% of the time. And then I'm slicing open a quarter of it so you can kind of see what's happening inside here, right? Because the wave function's kind of funny. It doesn't just go straight down. It goes down, and then it goes negative, and then it comes up again, all right? And this is what we call a node, right? Which is analogous to a node on a string, all right? So what that means is you have probability density here at very close to the nucleus, and then probability density out here a little further away from the nucleus. But then you have a 0 probability density right there at, what is this? 120 picometers or something like that, right? So this is kind of the dot representation up here. The dots are finer, but it's the same idea. So you have a high probability of finding it here. That corresponds to this. And then a node, which is this area where it's never found, and that corresponds to that. And then further out, you have probability density of finding it again, which corresponds to that bump. And then if we, instead of probability density, plot total radio probability, this tells you the total probability of finding the electron at a particular, in a particular thin spherical shell at a particular radius from the nucleus, right? So that total probability is 0 at the nucleus. It comes up, and then it goes down at the node, back to 0, and then it goes up again, and then it comes back down. When you go from the 2s to the 3s, it's very similar, except that first of all, the orbital is bigger. And secondly, instead of having just one node, there's actually 2 nodes. One here where the probability goes to 0, and one here where the probability goes to 0, right? And so you can find the electron close to the nucleus, and then there's a node, and then there's a ring of probability here in between two nodes, and then you have another node, and then you have more probability out here. Does that make sense?
Yeah, a lot more sense. I was just very it clicks now understanding the node relationship.
Yep.
Because before I was very lost. Okay, thank you.
Okay, good. Good. All right.
Wait, Joe. Yeah. Could you go back to those diagrams? I had a question on those diagrams.
Yeah. This one?
Yeah. Like how exactly does that work? Does that just mean like
Have you had multivariable calculus? Have you dealt with spherical coordinates?
I have not gotten there yet, but soon.
It's a little hard. It's a
Hopefully.
little hard if you understand spherical coordinates. If you have that, basically what we're doing here is we're, instead of x, y, and z, you can specify any point in 3 dimensions by a distance from the nucleus and then 2 angles. So let's just say we want to specify a position in this plane, in the xy plane, right? We can just specify distance from the nucleus and then some angle, right? Where we call x 0, y 90 degrees, let's say, and then this 180 degrees and so on.
Yeah.
So what happens here is if you were to plot psi as a function of this angle theta, it would go like this. It would go, right? So start here at 0, angle 0, and you have high probability. And then as you move out from there, the probability goes down. It goes down to 0 at 90 degrees at the y-axis. There's no probability. So that represents a node in the angle theta, right? And then as you keep going, it comes back up again, right? So that's 0, 0, 90 degrees, 180 degrees, 0, 90 degrees, 180 degrees, right? And then if you do psi squared, of course, it goes like this, right? So that node there is at 90 degrees, which is basically at the y-axis. Does that make sense?
Yeah, but my question is more specifically on for the example how